In this part of the lesson, I would like to develop Euler's method of approximation. To do that, we're first going to start with the linear approximation. L of x equals f of a plus f prime of a, x minus a. We've seen this a bunch of times. Now this, of course, is when dy dx is equal to f prime of x, meaning it depends on x alone. The derivative, that is, depends on x alone. Now, if the derivative depends on the x and the y, then it's still f of a plus f prime of, we'll say a, b, the ordered pair, times x minus a. So that's the linear approximation. Dy dx equals f prime of x and y. So here's a diagram of a function f of x together with a linear tangent. So I'll label this L of x. Now what Euler's approximation does is basically iterations of the linear approximation. So it starts at this point and then it says let's create a linear approximation, but it only goes up to a certain point for some determined change of x. So for some determined change of x, then it reiterates. It says what would the slope be if it went through this new point? Then I would calculate the slope there and do a linear approximation from there, going out the same change in x. Then we'd recalibrate, that's more like here, then we'd recalibrate, do the linear approximation yet again, but starting from this new point, what would the slope be if it were going through there and shoot out to here? So let's see if I can draw that change in x. So we can see that this is a better approximation, and certainly going to be an even better approximation if change in x is small and we have many of them. It can basically follow the contour of our function f of x. So iterations of the linear approximation is Euler's method. Let's look at some details. We're going to start at the point x naught comma y naught. That would be like right here, x naught y naught. From there, we're going to do a linear approximation. Let's say y hat 1. So the hat is an approximation. Y hat 1 will be the first y value, the y naught, plus, now we're going to find the derivative at that point, x naught comma y naught. Then we're going to take it out some distance, change in x. So this would give us what I've just highlighted there in white, ultimately pointing to a new point, which is x naught plus change in x, comma, y hat 1. That would be this point here. Then we do it again. Let's write the next point, which is x1 comma y hat 1, and our next linear approximation segment will be y hat 2, which will be the y hat 1 as a starting point, plus f prime at this x1 comma y hat 1, and again we'll go out change in x, which will bring us to this point here, which is x1 plus change in x, comma y hat 2. Continuing on, we have x2 comma y hat 2, y hat 3 is going to be the y hat 2, plus f prime at x2 comma y hat 2. Change in x, bringing us to x2 plus change in x, comma y hat 3. That would bring us out to here. We will now summarize by saying y hat n will equal y hat n minus 1 plus f prime at x n minus 1 comma y hat n minus 1 change in x. Euler's method is iterations of the linear approximations. Let's take a look at example 1. dy dx equals 2x. Y equals f of x is the solution function. that passes through the point 1.5, 4, which is that point right there. Part A is a review, a linear approximation. It calls for, centered at the point 1.5, to approximate f of 3. So L of x will be 4 plus f prime at 1.5, x minus 1.5. That will lead to 4 plus the slope at 1.5. If I plug 1.5 into my slope formula, I get 3, x minus 1.5. There is our linearization, our line tangent to the curve. We will say f of 3 is approximately L of 3, which will be 4 plus 3 times 3 minus 1.5 is 1.5. The linear approximation will be 8.5. We are estimating that at 3, the function's value will be approximately 8.5. The real value of the function is up here. That's going to be at the end of the problem. Part B. In Part B, we're going to use Euler's method of approximation to approximate f of 3. Our starting point, x0, y0, is the initial point, 1.5, 4. We will say now that y hat 1 will equal the 4 plus the slope at 1.5, so 2 times the 1.5. I put the slope in the bracket just to separate it nicely. And then it is predetermined. The author wants us to do change in x equals 0.5. So that gets tagged on the end. When I do the arithmetic, that comes out to be 5.5. So from the point 1.5 to 4, following the tangent line, that will point out to the coordinate 2, 5.5, which is our next starting point, 2, 5.5. Our second iteration, y hat 2 equals 5.5 plus the slope at 2, which is 2 times 2, and then our change in x. The arithmetic leads to 7.5. That will point out to 2.5, 7.5. Our new starting point, 2.5, 7.5. Y hat 3 will be the 7.5 plus the slope of 2 times 2.5. Once again, change in x. Arithmetic comes out to be 10. That will point us out to 3, 10. And that's how I know I'm going to stop. I wish to approximate f at 3, and I have that approximation here. F of 3 is approximately Euler's iterations at 3, which equals 10. In Part C, I've quickly solved the differential equation using the methods contained inside this lesson. Here we have our particular solution here. Therefore, f of 3 equals 3 squared plus 7/4, which comes out to be 43/4, 10.75. Just so we can look at that graphically. We found in Part C that the function at 3 is 10.75. When we used Euler's method of approximation, we went out a change in x of 0.5. So we followed this along for a change in x of 0.5. We reiterated, took another for 0.5, and yet another for 0.5. Euler's method came out to be 10. So that shot up to the 10. Euler's at 3 equals 10. Example 2, dy dx is 2x over 3y. Y equals f of x is the solution function that passes through the point 0.5, 1. Part A wants the linear approximation centered at 0.51 and wants to use that to approximate f of 1.5. L of x equals f of 0.5 plus f prime. The slope depends on the x and the y. So f prime at 0.5, 1, change in x, or x minus 0.5. Specifics, L of x equals 1 plus, now the slope is going to be 2 times the 0.5 all over 3 times the 1, x minus 0.5. I'll simplify that a little further still. L of x equals 1 plus a third, x minus 0.5. Here's our linear approximation. F at 1.5 is approximately the line tangent at 1.5, which comes out to be 1 plus 1/3 times, which equals 4/3. I would encourage you to try part B, Euler's method, starting at 0.5, 1. That's our starting point. I would encourage you to do this to find the answer. Arithmetic, no calculator, so you can get the experience of when to stop and practice the methodology. So press pause now and then come back for the solution. Okay, here we go. Y hat 1 is the 1 plus f prime at 0.5, 1. Change in x, 0.5. Let's do the arithmetic now. 1 plus, I'll put the slope in brackets to separate it, 2 times 0.5, 3 times 1, times the 0.5 change in x, which will come out to be 7/6. Our next point will be a change in x of 0.5, so that brings out to 1, 7/6. And our y hat 2 is the 7/6 plus f prime at 1, 7/6. Kind of tongue twister, which is going to be the 7/6 plus 2 times the 1 over 3 times the 7/6. Change in x of 0.5. That arithmetic comes out to be 61/42. That will point out then to 1.5, 61/42. That's how I know I can stop, because I've got my approximation at 1.5. F at 1.5 is approximately Euler's method at 1.5, which equals over 42, and I'm going to mark that in a moment. But first, I quickly ran through solving the particular solution at the given point, and we're going to find f at 1.5 to be exactly the square root of, I'm going to plug this in, do the arithmetic, it's going to be the square root of 7/3. And just so we can mark that, I'll tell you that's going to be approximately 1.527. We'll come up here, we'll take a look at these pieces. At 1.5, the real function is here. F at 1.5 is the square root of 7/3. The linear approximation was this value here. L of 1.5 was equal to 4/3, and somewhere in the middle we did iteration once, iteration twice, and that gives us that Euler's method at 1.5 was equal to 61/42.